Okay, today I'm going to talk about some recent progress in this topic of iterative machine teaching. First, I'd like to give you a brief introduction of what is machine teaching. And what I've drawn here is, in some sense, a summary of machine learning. Machine teaching is like inverse of machine learning. Okay. So essentially, for machine learning, you have algorithm A, and you have a data set. And what you want to learn is to learn the model based on the data, okay? So machine teaching is like you already have a model. The teacher already has a model, W star. And the teacher wants to transfer this model to a student model, okay? So the way that the teacher communicates with the student is just providing examples. So it's like the teacher has this W star in the model space. Assuming the student also use the same feature space. And you want to somehow transfer these W star to the student. But the way you can only communicate with the student is by providing examples smartly, okay? And then it's like furthermore, in the machine teaching case, typically the algorithm is also fixed. You fix the algorithm, assuming the student is using a particular way of learning. And you want to construct a set of examples. So the goal is to construct a small set of examples as small as possible, okay? This is the machine teaching, and then, so in last year, we sort of proposed these new concepts of iterative machine teaching. So in the previous slide, the data set are constructed in one shot, okay, and then provide to the student. Hopefully, the student can just use his own algorithm and work very hard on this example and learn the student model, learn the teacher model. But in the iterative machine teaching, and we will the student as an iterative algorithm, so there's an opportunity for us to provide example not in one shot, but in a sequential fashion and in a smart sequential way and provide example to the student. Essentially, the student can look at the teacher can look at a student's performance and determine what data point should be provided to the student. So once the student accepts this example, and he's going to update it with a fixed algorithm, and then the teacher can observe its performance again, and then provide another data point, okay? So in the previous iterative machine teaching, in that setting, essentially the teacher assumes that, the model assumes that the teacher knows about the student feature space, and the teacher even know about the current model the student has, okay? So essentially just pick examples trying to accelerate the learning process. Okay, so there are several cases actually. There are several different ways you can provide example to the student, and somehow it's categorized into these three categories. The first way to provide example to students is called the synthesis-based. In this case, the teacher has the freedom to cook out any examples in some space where the boundary radius are, okay? So synthesis-based. And then the second way of designing example, the teacher designing example is called the combination-based teaching. So essentially the teacher starts with a pool of examples, X in this data set D, and then it can perform some kind of weighted combination of these examples, existing examples. The third way of designing example by the teachers is we call it scaled pool-based teaching. So in this case, again, there's a pool of examples, D, and the teacher can only take the existing example and scale it down and up, scale the norm of these data points. In all these three cases, actually, you can show the teacher will be able to pick example intelligently, such that for the fixed algorithm the student has, you can actually make the student learn very fast. Yeah, so you can learn, if you want the student model to be epsilon close to the teacher model, you can actually get away with log 1 over epsilon examples. Okay. So, but in this previous iterative machine teaching model, there's a very strong assumption in the way the teacher obtains information from the student. In that model, we assume that the teacher actually know exactly what is student's feature representation, and it's the same as the teacher's feature representation, and you know exactly what is WT of the student status. Okay, so you just in some sense, you want to determine the sequence of dependent example to provide it to the student, such that the student's model WT can converge to the teacher model W star as fast as possible. Okay, you can show that you can converge very fast. So the intuition is actually very simple. What you do is you look at, for instance, so we'll assume that the student is using a stochastic gradient descent algorithm. Whenever the teacher provides an example to the student is going to perform the fixed update, okay, according to some loss functions. Suppose it's using, for instance, linear regression is a square loss, and logistic regression is that loss. And then the student is going to update his model with a fixed algorithm, okay? That's the key thing in this setting. And then if you look at the distance between student's model after one update to the teacher model. So it's like this comes from the stochastic gradient update. And then you can decompose the error into a few turns, yeah? And then these, essentially the first turn here is going to be computing something like the difficulty of the example, okay? So how far away is this student prediction from the true label, okay? Or the confidence level of the student in this case, if it is a classification. And the second turn is actually measuring in some sense, the gradient of that example, on that example, how well it aligns with the difference between the student and the teacher. Ideally, you want to pick example where the gradient aligns exactly with this desired descent direction, which is the difference between WT and W, yeah, okay? But there's a trade-off between the two turns. So there's a eta and eta square trade-off between these two turns. So one turn is the difficulty level, and the other turn is how well it aligns with the gradient desired descent direction. So typically these initial stage, actually this turn is going to play the key role, okay? The second turn will be, the magnitude will be smaller. So essentially you want to minimize, there's a trade-off between the example, between these two turns, depending on the example you pick. So overall you want to minimize the summation of these two turns such that in error iteration, the reduction in the distance between the W and W star is the largest, okay? So a very intuitive idea is just to pick an example which, so here is flipping the sign, so it's minimizing this, okay? You want to pick an example which balances the two turn. And that's how you actually pick the example, okay? So in fact, the sort of paradigm algorithm is very simple. In every step, when you try to determine whether you want to pick example, you will just essentially solve optimization problem. You will pick those examples dependently. So, but now the more challenging case is what if the teacher don't get to observe the student parameter WT, and in the more complicated cases, sometimes the teacher's feature space and student teacher space are not the same, okay? So that's the new setting we call the cross-space machine teaching. So the teacher's feature space and student feature space may not be the same. And also you don't get to observe exactly the teacher's parameter WT. You only get to query the student by asking questions, okay? The student will return you the inner product between his WT and then the data point inputs, and potentially after a transformation F, okay? So that's the cross-space iterative machine teaching problem. And if you don't place any assumption on these transformation F, so essentially it becomes a black box result. We have some result for this cross-space iterative teaching case. We haven't solved the most general case when F is something you don't know, okay? So I will just provide some high-level idea of the approach, and then the detail you can go to the poster. So the high-level idea of these new result is when the teacher is interacting with the student, okay, since you don't have the student model anymore, and then the teacher will try to estimate or maintain a student model, okay, using active learning in some sense, okay? Then the teacher is going to design example according to this virtual student model he's maintaining. Okay, very similar to the real case when the teacher is teaching some real student. You cannot open up the brain of the student and ask what is the WT. Okay, then the teacher has to somehow maintain a model of his own about where the student is in this parameter space. And then you're going to design example according to this virtual model that maintain the teacher space. So I'm going to skip these slides. And in this case, essentially, you can also prove the exponential improvement if you have these, in some sense, the maintain this virtual student model. Okay. So this is some experimental results. You can show that even the teacher don't have access to the student model exactly, but using this actively maintained student model, you can still achieve exponential convergence. Okay, yeah. So in the end, I'd like to conclude. In some sense, you can think about these student model maintained by the teacher, and is done by querying the student. It's like exam to the student. That step is very important for the case when the teacher doesn't have exact access to the student model in the black box teaching case. If you're interested in the detail, this work is more theoretical in nature. You can come to the poster. Okay, that's it. Thank you. Question. Okay.
For the video?
Hi, very interesting presentation. Just one question. Does that mean that the quality of the student model is actually will be bounded by the teacher's model? That means the quality of the student's model will not surpass the teacher's model.
So in this case, we didn't consider the most general case, the student can surpass the teacher performance. So now we are more like wanting to transfer the teacher's knowledge to the student's knowledge. And that's the goal here, right? Yeah, we didn't consider a case when the student can train with some additional data and maybe do better than the teacher's model, right?
Okay, so this is kind of the heritage, like where students' model will inherit from the.
That's
is that kind of kind of the transfer learning?
So you can view it as some kind of transfer learning. So another application could be in security case, and then the adversarial wants the machine learning model to learn something he designed. Okay, right. And then but you want to somehow interact with the machine learning system with a small number of iterations. So this is another setting, cybersecurity setting, right? Transfer learning is another, yeah.
Okay. Mm-hmm. So is there any comparison between, sorry, just last question. Is there any comparison between the imitation learning that we have saw at the very beginning of these conferences? Is there any connection in between?
In some sense, you can formulate this as some kind of reinforcement imitation learning problem. But in this case, the problem structure is simpler. Okay, you can actually analyze the behavior of these model, and then get some kind of finite sample guarantee. For the real-world imitation learning case, it's very complicated to get any sample complexity analysis.
Thank you very much. Sorry for a 2-minute question.
Very different question. So since this is motivated by the sort of real education in the background a bit, I was wondering if one of the future things to look at would be to include multiple students who learn from each other, perhaps on the co-training or co-testing model, in between talking to the teacher. Because that's very much part of the real education as well. Right?
Yeah, that's
and
very
there is co-training for that, and indeed this idea of cross-space representation is there in co-training very much.
Yeah, so this is a very interesting question. We actually haven't worked too much into that real-world scenario yet. So every student may have a different feature representation. And now you have to think about picking an example, because very often, if it's not personalized tutoring, you're providing the same example to a bunch of students. There's a distribution in some sense. And how to pick the best example, again, we don't know, right? There are lots of interesting theoretical questions you can investigate. Yeah.
Let's thank the speaker again.